Chapter 5 introduces the idea of vector spaces, generalizing what we call a vector and what we can use to define addition and scalar multiplication so that certain rules apply. Consequently, we can think of a matrix now as a set of vectors, whether it's in rows or columns, talk about the solution space as a set of vectors as well, and therefore bringing up the idea of if these vectors are linearly independent, if a combination of them can span a certain space, the bases that can be represented by the vectors, and the dimensions. I will go through all this vocabulary, probably combining a lot of ideas together because they're so interrelated. Let's start with the idea of a vector space. So I have here two different definitions that I want to prove or disprove if they can be representing vector spaces or not. Basically, a vector space has to follow four different ideas, or actually I guess 5 different ideas, to see if it actually works. And I'll go through with the first one all the different ideas. So first, a vector space has to satisfy the property of closure. Basically meaning if I were to operate on this with addition or scalar multiplication, I still define items within the same space. So for example, if I were to add two vectors, x1, y1, plus x2, y2, I want to make sure the result is something that is still in R2 because I define my vectors as two-dimensional vectors. And in this case, it is true. Same thing with scalar multiplication. If I multiply a vector by a scalar, kx1, y1, I get kx1 and y1. And this is still an element of R2, and therefore it is closed in the scalar multiplication. That's one of the properties that a vector space has to satisfy. Another property is the idea of commutative and associative property. Commutative is specifically for addition. I want to make sure if I add x1, y1 plus x2, y2, that this is the same as if I were to add x2, y2 plus x1, y1. In this case it is true because in both cases I get x1 plus x2 and y1 plus y2. That's the idea of commutative. Associative means I can regroup. So if I have x1, y1 plus the quantity of x2, y2 plus x3, y3, this would be the same as if I were to group x1 and y1 plus x2, y2 and added that result to x3 and y3. And again, in this case of this defined addition, this is still true because this is equal to x1 plus x2 plus x3, y1 plus y2 plus y3. But associativity also has to work with the scalar multiplication, meaning that if I have two scalars, such as k and L times my vector, x1, y1. Let's just do xy. This would equal L times k of xy, and that has to also equal the scalars multiplied together times xy. So let's compare all of these. This here, the very first one would be k of Lx, y, and then one more scalar multiplication would make this klx, y. Likewise, the second one, or the middle one, would be lkx, y, and then the last one would be lkx, y. So associativity and commutative properties still hold. The third property for a vector space is that it has to satisfy the additive identity, the additive inverse, and the multiplicative identity. The additive identity is that if I take a vector, xy, there should be some vector that I can add to it and still get xy. This is true because I can have the vector 0, 0, which is in R2, and xy plus 0, 0 is still xy. So there is the additive identity. The additive inverse says I can take xy plus the vector defined in the space and get the additive inverse. This is also true because my additive identity can be the opposite of x and the opposite of y. Lastly is the multiplicative identity. The multiplicative identity states that I can take 1 times xy and still get xy. And in this case it's true because you get 1x comma y, which is xy. So the additive identity, the additive inverse, and the multiplicative identity, all those properties hold as well. The last property we want to look at is the idea of distributive. And there are two types of distributive that we want to make sure are still true. We want to make sure that if we were to distribute a scalar, for example, k plus L times xy, this would equal k times xy plus L times xy. So if I use my definition of scalar multiplication, the left side is going to equal k plus L x comma y. The right hand side is going to equal kx comma y plus lx comma y. Adding these together, I get kx plus lx comma 2y. If I factor out the x, I get k plus l x comma 2y. But notice these two are actually not equal, and so this distributive property does not hold. Looking at the other distributive property, the other distributive property is if I were to distribute the vector. So k of x1 comma y1 plus x2 comma y2 should equal k times x1 y1 plus k times x2 comma y2. So again, using the expression on the left, I would have k times x1 plus x2 comma y1 plus y2 equals kx comma y1 plus kx2 comma y2. And then continuing, the left side would equal kx1 plus x2 comma y1 plus y2. The right side would equal kx1 plus kx2 comma y1 plus y2. So that distributive property actually holds, and it's the one that I just did before this that doesn't hold. So this is not a vector space. Let's continue with the second example. Now, a good way to look at this is to look at the definitions for addition and scalar multiplication and see which is different from our normal addition and multiplication. Notice here, scalar multiplication appears normally. So what I want to focus on are the properties that involve addition. Let's start with closure. Closure says if I add two vectors, is the result, in this case, still an R2 vector? And it is. Second property, commutative. Commutative says x1 comma y1 plus x2 comma y2 must equal x2 comma x1 or x2 comma y2 plus x1 comma y1. But using our definition of addition, this is not true because we get x1 minus x2 comma y1 plus y2 is not equal to x2 minus x1 comma y2 plus y1. So commutative property does not hold. Associative property. Associative property says x1, comma y1 plus the grouping of x2, comma y2 plus x3, comma y3 should equal the grouping of x1, comma y1 plus x2, comma y2 minus x3, comma y3. So if I use this idea of addition that I've defined, this would be x1, comma y1 plus x2 minus x3, comma y2 plus y3. And then one more addition would make this x1 minus the quantity x2 plus x3, because I would subtract both of them, and y1 plus y2 plus y3. However, on the right-hand side, I would get x1 minus x2 minus, minus x3, and then y1 plus y2 plus y3. So these components here are different, and therefore the associative property is not satisfied either. I still have an additive identity because xy plus 0, 0 is still xy. I still have an additive inverse. So additive inverse is xy plus something something equals 0, comma 0. In this case, the additive inverse is going to be x, comma negative y. And we can check our distributive properties. So if I have k times x1, comma y1 plus x2, comma y2, I'm going to get k x2 x1 minus k x2, comma ky one plus ky two. And that is equivalent to kx1, comma y1 plus k times x2, comma y2. So that distributive property still holds. If I do k plus l times xy, I'm going to get k plus l times x, comma y. But if I do kxy plus lxy, I get kxy plus lx, comma y. And then in subtracting, I get kx minus lx, comma 2y. Which is not equal, oh, sorry. This is kx, ky, lx, ly. So this would be k plus ly. So k plus ly. And then up here, this is also k plus ly. So again, this is not the same because here I have kx minus lx, here I have kx plus lx. So this particular distributive property does not work either. And again, notice I focused only on the addition ones because the addition of the vector space was defined differently. Alright. Subspaces are basically subcategories of vector spaces. You want to make sure all the properties apply. So distributive, identity, additive inverse, all of those should be applicable already. But because it is a subset, the most important thing you want to check is that it is actually closed in that system. So for example, in this first one here, the set of all 2 by 2 matrices of the form A0, BC, such that B equals 3A plus 2C, is still a subspace of M22. So basically, I want to focus on the idea of closed. So if I take two matrices, A1, 0, B1, and C1, add it to A2, 0, B2, and C2, so we'll assume normal addition and scalar multiplication for our matrices. I get A1 plus A2, 0, B1 plus B2, and C1 plus C2. But I want to make sure that even after I add them, this property here is still true. So I know that B1 equals 3a1 plus 2c1. I know that b2 equals 3a2 plus 2c2. So if I add these together, I get b1 plus b2 equals 3 times a1 plus 2c1 plus 3a2 plus 2c2, which is equal to 3 times the quantity a1 plus a2 plus 2 times the quantity c1 plus c2, which is exactly what I need for the sum part. So, closed under addition. Now, I need to check if it's closed under scalar multiplication. So, scalar multiplication would require that k times a0 bc, and again, we'll assume normal scalar multiplication properties, ka 0 kb kc still satisfies the relationship that I underlined in red. So I know that b equals 3a plus 2c. If I multiply b by k, I get kb equals k times 3a plus 2c. But that equals k times, or 3 times ka plus 2 times kc, which again satisfies this. So it's closed under addition and scalar multiplication, and that makes this first example a subspace. Looking at the second example, if I pick two polynomials with at least one real root, is this still a subspace of basically quadratic polynomials? This one is actually not closed under addition. And if you kind of think about it, it makes sense that if I add two polynomials, that doesn't guarantee that there's at least one root. Now you want to give me a counterexample. So for example, if I make p of 1x equal to x squared minus 2x plus 1, if I make p sub 2x equal to x squared plus 2x, this first one has one root, the second polynomial has two roots, and therefore satisfies the conditions that I have of having at least one real root. But if I were to add them, p1 plus p2 would equal 2x squared plus 1, and this has no roots. So, not closed under scalar multiplication. Or, I'm sorry, not closed under addition. Now let's take a look at our other vocabulary, the idea of how we can relate vectors to each other and use vectors to categorize things like bases and dimensions. The first thing I want to start with is I have three polynomials here, and I want to show that they represent a basis in P2. Basically what that means, I'm going to go straight from the very beginning, is that they have to be linearly independent. If it's a basis, it has to be linearly independent, and it has to span all of P2. So I'm going to use this to review linearly independence. Linearly independence means if I take C1 times 2x plus C2 times 5x minus 8x squared plus C3 times 7x plus 1, and I set this equal to the 0 vector, this automatically means it's only true if C1 equals C2 equals C3 equals 0 identically. And again, you can't just substitute in zeros and say that equals 0. The idea is you're solving for C1, C2, and C3. So I'm going to rewrite this as a matrix problem. I'm going to take each of these polynomials and think of it as a vector so that I can put it in a matrix. I'm going to put them in as columns. So the first one is going to be 0, 2, and 0. I'm going to make my first element the cubic coefficient, the quadratic coefficient, the second element the linear coefficient, and the last element my constant. So if I follow that same order, my next column is going to be negative 8, 5, and 0, and then my last column is going to be 0, 7, and 1. And I want this times C1, C2, C3 to equal 0, 0, 0. So if you were to multiply this out, notice how we get negative 8 C2 has to equal 0, which makes sense from up here, because you see a negative 8x squared times C2 has to equal 0. The next column will be 2C1 plus 5C2 plus 7C3 has to equal 0, and those are my linear terms. So here's my 2C1, my 5C2, and my 7C3, and it has to equal 0 as well. So I'm going to set this up as an RREF, 0, negative 8, 0. 2, 5, 7, 0, 0, 1, 0, 0, 0. RREF this, and I get 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. So reading the solutions, this means C1 equals 0, C2 equals 0, and C3 equals 0, and therefore these vectors are linearly independent. The idea of span is that if I have a linear combination, and I don't want to use C to confuse it with the linearly independent, but let's say I have something like D1 times 2x plus D2 times 5x minus 8x squared plus D3 times 7x plus 1 equals B, then there is a solution for any B in P2. So for any quadratic polynomial, basically I can find a linear combination of 2x, 5x minus 8x squared, and 7x plus 1 that can represent that polynomial. So this matrix would be set up the following way. It would still be 0, negative 8, 0, 2, 5, 7, 0, 0, 1. This time I'm going to use D1, D2, and D3. And it basically equals any quadratic polynomial. So I'll represent that as B2, B1, B2, and B3. And again, remember, these are just representing the coefficients. They're not actually representing the vectors. Now this one I'm going to RREF as well. So I'm going to go ahead and start scrambling it. 2, 5, 7, 0, negative 8, 0, 0, 0, 1. And since I scrambled it, this becomes B2, B1, B3. This one I'm going to do by hand because of the letters there. So for example, you would take R2 and divide it by negative 8. And then you would do, for example, R1 minus 7 R3s. So if I do that, I'm going to have 2, 5, 0, B2 minus 7 B3, 0, 1, 0, B1 divided by negative 8, 0, 0, 1. And this is B3. So I'm going to put a couple of steps together here. I'm going to do R1 minus 5 R2. And I'm going to divide that result by 2. And then I'm going to leave the others 2 alone. So now I have the identity 1, 0, 0, 0, 1, 0, 0, 0, 1. And my right hand side becomes B2 minus 7B3 minus 5 of B1 over negative 8 all over 2. B1 divided by negative 8 and B3. So as you can see, I have solutions for D1, D2, and D3. D1 would equal B2 minus 7B3 plus 5/8 B1 all over 2. D2 would equal negative B1 over 8, and D3 would equal B3. So since there's a solution for D, for any B vector that I define, this means it spans P2. Now, keep in mind that basically what I'm doing with both of these is I have, in one case, AX equals 0. In another case, I have AX equals B. And I basically want to make sure that both are consistent. So if I want to do this together, that basically means that A inverse must exist. And that means the determinant of A cannot equal 0. So a way to prove this simultaneously would be to find the determinant of A. And if I find the determinant of A of 0, negative 8, 0, 2, 5, 7, 0, 0, 1, I get 16, which is not equal to 0, and therefore this is a basis. Now, a couple of things. It's a basis. The dimension is the number of basis vectors. So in this case, our dimension is 3. Okay, in section 5, we talked about the idea of row space, column space, and then in section 6, we talked about rank and nullity. So I'm going to try to put the two ideas together. I have a matrix here, A. First thing I'm going to do is to RREF it. So if I RREF A, I get 1, 0, -1, -2, 0, 1, 2, 3, 0, 0, 0, 0. Now, in section 5, we learned that we can think of as a matrix as a set of two different ideas, either as a set of row vectors or a set of column vectors. And consequently, the set of row vectors define a row space, and the column vectors define a column space. And if we do row operations on it, what we can do is basically reduce it down to the basis for the row space, and also talk about the basis for the column space. So here's my RAF. What I've done is I've taken away all the linear combinations basically that are possible. And so the basis for the row space of A would be the vectors 1, 0, -1, -2, and 0, 1, 2, and 3. Now, the basis for the column space is not as straightforward, but not too bad either. Because the idea is you might have done a row interchange, in which case you change the order of the components in the column, and therefore I can't say 1, 0, 0, and 0, 1, 0 are necessarily the basis for my column space. However, the leading ones can refer back to the original columns that I can then use for the column space. So the leading ones are in column 1 and column 2. So column 1, 1, 1, 4, and column 2 of my original matrix would be the basis for my column space. And in fact, I can use the other two columns to talk about the other linear combinations. So I know that column 3 is -1 of column 1 plus twice column 2. And I know that column 4 is -2 times column 1 plus 3 times column 2. We also talked about the idea of the rank of A, which is basically the dimension of the row space of A. And so in this case, since there's two vectors, the rank of A is 2. The nullity of A would be the number of columns minus the rank. So in this case, there's 4 columns minus 2. The nullity of A is 2. Now, suppose I want the basis for the row space in terms of the original rows. What I do in that case is I look at the RREF of A transpose. So if I RREF A transpose, I get 1, 0, 5, 0, 1, -1, 0, 0, 0, 0, 0, 0. Now, we got to kind of think of this backwards. So, the row space of A would be the column space of A transpose. So, the column space of A transpose, so let's take column 1 and column 2 of A transpose, which would be row 1 and row 2 of A, and that would be the row space of A, which is the column space of A transpose. And basically those would be the first two rows then of A, which would be 1, 1, 1, 1. And 1, 2, 3, 4. The row space of A transpose would be the same as the column space of A. And so the row space, remember, I just read normally. So that would be 1, 0, 5 and 0, 1, -1. Now, just to kind of review the other things, the rank of A transpose, which is the dimension of the row space, and the dimension of the column space is 2. The nullity of A transpose is the number of rows of A minus the rank of A transpose. And in this case, that's going to be 1. So, if you recall, the rank of A transpose is always equal to the rank of A, because the dimension of the column space is always equal to the dimension of the row space. The nullity idea comes from our null space idea. So going all the way up here, and remember, these represent my solution, this represents my null space, so the null space is 2 in that case, and the nullity is 2. Same thing here, this represents my solution, this represents my null space, and so in this case the null space is 1, and therefore the nullity is 1 as well. Alright, so I jumped the gun. So here's my solution space. I want to use this to talk about solution space and null space. I have an A and I have a B, and I'm going to go back to the basics and basically solve AX equals B. So if I set this up as an augmented matrix, 1, 1, 1, 1, 1, 2, 3, 4, 4, 3, 2, 1, augment it with 14, 35, and 35, and do an RREF with this, I'm going to end up with 1, 0, negative 1, negative 2, that should look familiar, negative 7, 0, 1, 2, 3, 21, 0, 0, 0, 0, 0. Now if I translate this back into an equation, it means that x1 minus x3 minus 2x4 equals 7. It means that x2 plus 2x3 plus 3x4 equals 21. So if I write my solution vector x1, x2, x3, and x4, substituting, I can rewrite x1 as x3 plus 2x4 plus 7. I can write x2 as negative 2x3 minus 3x4 plus 21. And then I still have my x3 and my x4 component because they're basically my parameters. Now I can separate this into 3 vectors. I have a, what I call a constant vector, 7, oh, sorry, this should be a negative 7, yeah, negative 7. So negative 7 and 21, 0, 0. Then I have a vector that's being multiplied by x3, so that would be 1, negative 2, 1, and 0. And then another vector being multiplied by x4, 2, negative 3, 0, and 1. So let's label. This first piece here is called the particular solution. If I were to take my matrix A and multiply it by xp, I would get the actual solution of 14, or I would get the result 14, 35, and 35. So xp is actually what's generating the numerical values. These here are what I call the homogeneous, or what I call the null space solutions, because if I were to take A times x sub 0, I would get the 0 vector. But the fact is that A is a linear transformation, so if you do A times xp plus xh, that's the same as A times xp plus A times xh. A times xp is 14, 35, and 35. A times xh is 0, 0, 0. And you get 14, 35, and 35. So that's why any solution is actually made up of 2 components, a particular solution and a homogeneous component. Okay, let's keep practicing our vocabulary. So I have here again 2 polynomials, p1 and p2, in a cubic polynomial vector space. And the first question I have is this cubic polynomial I have, negative 8x cubed minus 2x squared plus 12x minus 6, in the span of p1x and p2x? So span basically means that it can be represented by a linear combination of p1 and p2. So I am going to set up my matrix in the following manner. I'm going to set up a matrix 3, 0, negative 4, 1, 0, 5, 0, 2, and I'm going to augment that with negative 8, negative 2, 12, and negative 6. So if I do the RREF on this, I get 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. Reading this third row, this would mean that 0C1 plus 0C2 equals 1, which means there is no solution, and therefore it's not in the span. So the question is, can I define two vectors to complete a basis for P3? If I think about P3, all cubic polynomials, the most simplest basis set I could have for this would be a constant, a linear term, a quadratic, and a cubic. So I need two vectors to work this out. Since the vectors have to be linearly independent, probably the easiest way to set this up would be if I could define two vectors orthogonal to the ones that I'm interested in, which means I need a dot product of 0. So I'm going to set up now 3, 0, negative 4, 1 as a row, so that if I multiply it by x1, x2, x3, and x4, I generate a dot product when I multiply those together. Similarly, I'm going to set up 0, 5, 0, 2 as my second row, and since I want these to be independent, I'm going to set their dot products up to 0. So I'm basically augmenting 3, 0, negative 4, 1, 0. 0, 5, 0, 2, and 0. So if I RREF this, I get 1, 0, negative 4 thirds, 1 third, and 0. 0, 1, 0, and 2 fifths, and 0. That is a 3. Okay, again, translating these solutions, this would mean that x1 is equal to 4 thirds x3 minus 1 third x4. And x2 equals negative 2 fifths x4. So my solution vector would be x1, which is 4 thirds x2, minus 1 third x4, negative 2 fifths x4, x3, and x4. And then if I separate this into a linear combination of x3 and x4, I would have 4 fifths, 0, 1, and 0. Oh, I'm sorry, I think that's 4 thirds. 4 thirds. That one times x3, that's 4 thirds, plus negative 1 third, negative 2 fifths, 0, and 1 times x4. So my two linearly independent vectors would be 4 thirds, 0, 1, and 0, and negative 1 third, negative 2 fifths, 0, and 1. Now, a couple of things I'm going to mention. One, since it could be any scalar of this, and I'm not a big fan of fractions, I'm going to rescale this. So I'm going to change this first vector by multiplying by 3 to be 4, 0, 3, 0. And then I'm going to do likewise and change my second one by multiplying by negative 15. So this will be 5, 6, 0, and negative 15. But one last thing, those aren't my final answers, because if you recall, my original vectors way up here were polynomials, and I just turned it into a matrix of coefficients to make it easy to work with. So my final vectors I need to make sure are still polynomials. So my final answers are actually p of 3 of x is going to equal 4x cubed plus 3x, and p4 of x is going to equal 5x cubed plus 6x minus 15. So make sure your vectors are all consistent in their forms. The whole idea of rewriting it as a column vector is basically so you can do things like RREF to help solve it. Now, let's do something similar with matrices. I'm going to approach this one a little bit differently. So first, I've got three matrices that are set S. I want to find V4 so that I can represent a basis in any 2 by 2 matrix. So a standard basis for M22 would basically be something like 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. So the dimension would be 4. So if I only have 3 2 by 2 matrices here, I need a fourth matrix. Now, if you think all the way back to when I talked about linearly independent and span, I said if the determinant was not equal to 0, then they would span. And they would also be linearly independent. So let's do that way for this one instead. I have 2, negative 3, 0, 5. So same thing. I'm going to stretch this out so I can use the ideas of matrices to help me solve for it. So then similarly, the next column will be 5, 1, negative 1, 6, 1, 1, 1, 1. And then my missing vector, I'm going to put in A, B, C, D. And I basically want to solve this so that it's not equal to 0. So if I find a relationship with this, with my calculator, I get 31A minus 16B plus 7C minus 21D cannot equal 0. So basically I need to define an A, B, C, and D so that it's not equal to 0. How about if I just use 1, 0, 0, 0 for A, B, C, and D? Okay. But again, my original vectors were matrices, 2 by 2s, so I want to rewrite this as a matrix. So V4 is actually going to be the matrix 1, 0, 0, 0. Now that I have a basis, let's talk about coordinate systems. First one, I have 1, negative 3, 5, 8 relative to S, and I want to change to standard M22 form. So really, this isn't 1, negative 3, 5, 8 like we normally think of. This is 1 V1 and negative 3 V2s and 5 V3s and 8 V4s. And I want to use my V4 from above. So 1, negative 3, 5, 8 relative to S is actually 1 times V1 minus 3 times V2 plus 5 times V3 plus 8 times V4. So if I use all the matrices that I have defined above and add 1 of V1 minus 3 of V2 plus 5 of V3 plus 8 of V4, I get the matrix 0, negative 1, 8, and negative 8. So that is what it should have been if I was in my normal standard matrix form of 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Now let's go in the reverse. So the reverse says, okay, I have 1, negative 3, 5, 8. I want to know what this coordinate would be with relative to S. So the question is now, how many V1s plus how many V2s plus how many V3s plus how many V4s are necessary to equal 1, negative 3, 5, and 8. So I'm going to stretch this out, make this 2, negative 3, 0, and 5, 5, 1, negative 1, 6, 1, 1, 1, 1, and the new one I defined, 1, 0, 0, 0, times C1, C2, C3, C4 equals 1, negative 3, 5, 8. And if I solve this, I get C1, C2, C3, and C4 to equal 2, negative 1, 4, and negative 2. So my coordinates relative to S are 2, negative 1, 4, negative 2 relative to S. And actually, I need to go back here and fix this because this is a coordinate system. So it's actually not a matrix, it's a set of coordinates. And so if I get 0, negative 1, 8, and 8, negative 8 for my coordinates. So basically 0 of my 1, 0, 0, 0 matrix, negative 1 of the next one, 8 of the next one, and negative 8 of my 0, 0, 0, 1 matrix. Lastly, I want to talk about the Wronskians. So basically a way to determine if a set of functions are linearly independent, what we're going to do is look at a Wronskian. A Wronskian in general looks like this. You have your three functions, f, g, and h, and then the next row is their derivatives, and then their second derivatives. And basically what you're doing is you're building a square matrix that you can take the derivative of. If the derivative is equal to 0 for all x, then it is linearly dependent. So I'm going to set up a Wronskian for this one. My first row is going to be my functions, so 2 to the x, 2 to the 3 plus x, and 4 to the x. Next row will be my first derivatives. So 2 to the x, ln of 2, 2 to the 3 plus x, ln of 2, 4 to the x, ln of 4. And then my last row is going to be my second derivatives. So 2 to the x, ln of 2 squared, 2 to the 3 plus x, ln of 2 squared, and 4 to the x, natural log of 4 squared. And I need to take the determinant of this. Now I am actually going to change this to its transpose. So 2 to the x, ln of 2, 2 to the x, natural log of 2 squared, 2 to the 3 plus x, 2 to the 3 plus x, natural log of 2, 4 to the x, natural log of 4, 2 to the x, I think I got this backwards. So 2 to the x, yes, I got carried away. Okay, so 2 to the 3 plus x, ln of 2, this should be 2 to the 3 plus x, natural log of 2 squared. And then this is 4 to the x, 4 to the x, natural log of 4, 4 to the x, natural log of 4 squared. Now, I changed it to its transpose because the determinant of A is equal to the determinant of A transpose. Plus, I can do some of that factoring stuff that we did back in chapter 2. So I'm going to factor out a 2 to the x, and a 2 to the 3 plus x, and a 4 to the x out of the first, second, and third rows in that order. So I will have 1 ln of 2, ln of 2 squared, 1 ln of 2, ln of 2 squared, 1 ln of 4, and ln of 4 squared. And I have two rows that are identical, which means this is equal to 0, and therefore these are linearly dependent. But you could have guessed that because 2 to the x and 2 to the 3 plus x, but 2 to the 3 plus x is the same as 8 times 2 to the x, so these are obviously linearly dependent to each other. Now, if I could just take a subset of this, I'll show you what it would look like possibly otherwise. So let's say we had 2 to the x and 4 to the x. Obviously not linearly dependent on each other because 4 to the x is equal to 2 to the 2x, so completely different. So if I did a Wronskian with this, I would have 2 to the x, 4 to the x, 2 to the x, natural log of 2, 4 to the x, natural log of 4. And if I took the determinant of this, I would have 2 to the x, 4 to the x, ln of 4, minus 2 to the x, 4 to the x, ln of 2, which equals 2 to the x, 4 to the x, natural log of 4, natural log of 2, which is not equal to 0 for all x. Now, if it equals 0 for one value of x, that's okay. The idea is that you don't want it to equal 0 for every possible value of x that you put in. So since this is not equal to 0 for all of x, these are linearly independent. And that wraps up chapter 5.